In this video, we're going to start looking at a couple different ways to find Hamilton paths and circuits. Alright, so here's our application. We looked at the pizza delivery route person, and we were interested in a delivery route that started and ended at the pizza place and visits every destination exactly once. This is an example of what's called a traveling salesperson problem. This is a general category that we would discuss in graph theory. And this would encompass all sorts of problems, but one example that gave this type of problem its name is a traveling salesperson who travels for business. So let's say that somebody wants to visit all of their clients or accounts in the most efficient way possible. Now that could refer to the most efficient time, the most efficient mileage, or maybe even the most efficient cost of travel. Alright, so to answer this type of question, we use what are called complete weighted graphs. So we do draw graphs, but we're also interested in factoring in what it means to be efficient. Okay, these numbers are called weights, and we assign numbers or weights to the edges of the graph, and these represent distances, maybe travel times, could be a cost of a flight, or anything else that would be relevant to the situation. So here's an example. Let's say we have 4 cities: Adamsburg, Irwin, Penn, and Trafford. And then we've weighted all of these graphs with numbers, and maybe these represent miles between the cities. Okay, so that would be a complete weighted graph. And then complete, we've talked about that. It means that all of the vertices are connected to all of the other vertices. And you can see that that is the case in this graph. Alright, so let's draw a complete weighted graph. So we have the distance in miles between 4 cities shown in this table. These are cities in New York. Alright, so the graph would need to have vertices for those 4 cities. So we've got Corning, Mansfield, Elmira, and Towanda. Okay. Now it's a complete graph, so I'm going to connect all of the vertices to all of the other vertices. Alright, so this would be for situations where it is possible to get to any of those cities from the other cities. And then we have all of the distances. And then notice we have this blank diagonal, so the distance from Corning to Corning isn't, is 0 or not calculated, so we don't need that. And then we go through and just label the distances. Alright, so from on the edge from Corning to Mansfield, we know that that's 30 miles. Mansfield to Elmira is 35 miles. Elmira and Towanda are 37 miles apart. Towanda and Corning, that's 54. Towanda and Mansfield is 38. And Corning and Elmira is 21. Okay, so what are the pros and cons of this? It is a little bit more work to draw the graph if you already have the table, but an advantage is that this is a more visual way of seeing this, and it also eliminates some of the redundant information. So if I know that Elmira to Mansfield is 35 miles, then in this table it also has to represent Mansfield to Elmira, but really that's the same number. So if I'm just concerned with the total distance, then maybe I prefer this graphical representation where I only have that piece of information listed once. Alright, so what do we do with these complete weighted graphs? Well, maybe we can quickly see at a glance whether or not something is the most efficient route. So let's say that there's a salesperson that lives in Adamsburg. Okay, so they want to start and end at there. And they want to travel from Adamsburg to Trafford, Trafford to Irwin, Irwin to Penn, and then home. Now this does hit all of those cities, but the question is this the most efficient route? Alright, so maybe you can quickly look through this graph and decide whether or not that would work, or whether or not there's a shorter route in terms of miles. Okay, So the optimal solution for a traveling salesperson problem is a Hamilton circuit for a complete weighted graph for which the sum of the weights of the edges traversed is the smallest possible number. Okay, so we're looking for a Hamilton circuit, meaning it begins and ends at the same vertex and hits all of the other vertices. And we want the sum of the weights to be the smallest possible number. Okay, so here's one way to find this optimal solution. We find the total weights for all possible Hamilton circuits and then just choose the smallest one. All right, this is called the brute force method, and that's because it is just that. You're just using brute force, no real tricky or clever method here, but you're just listing all the possible options out and then finding the optimal one. Okay, so we draw a complete weighted graph, list all possible Hamilton circuits, find the sum of all the weights, and then choose the smallest one. So let's try it out on this problem. The driving times in minutes between 4 cities are shown in this graph. Find the optimal solution for a copy machine repair technician starting in City A who has to visit a location in each city, that's the Hamilton circuit part, and wants to minimize driving time. Okay, so we need to list all Hamilton circuits that begin and end at A. All right, well, how many are there? So let's count vertices first. We have 4 vertices, so that means that there are 4 minus 1 factorial Hamilton circuits. Okay, that's 3 factorial, or 6 circuits. And you can see that this would be kind of a painful method. As soon as I get to even 5 vertices, there would already be 24 Hamilton circuits that we'd have to list. Okay, so what are they? Well, we know we need to begin and end at A. All right, and then I need to hit the other 3 cities, B, C, and D, somewhere in the middle. So I need to look at all of the different possible orders for those cities. Now, I like this problem because I think you can see the connection to the formula. Why are we ending up with 3 factorial Hamilton circuits here? Well, this is actually a question that we've answered before in when we looked at counting methods. The question could be rephrased. What we're really asking is how many different permutations are there of the letters B, C, and D, right? So I've got to fill those 3 letters into these 3 spots in some way. And we looked at permutations. We also looked at the fundamental counting principle. All right, so there are 3 vertices, and I want to look at permutations of all 3 of them. Or another way of saying it is, okay, there are 3 options for what city I could go to from A. Then that leaves 2 left to go to next, and then 1, and there it is. There's that 3 factorial that gives the 6 different circuits. All right, so if you're fixing a beginning and ending point, okay, then that also explains why we have a factorial, like 3 factorial and not 4 factorial, because we've already used one of those vertices for the beginning and the ending. Okay, so what are they? Well, we've got 3 options for what city could come next. Okay, so it could be B, or it could be C, or it could be D. Okay, and if it's B, then we could do CD next. All right, or I could do DC. Okay, if it's C, then I could do BD, or I could do DB. Okay, and then if it's D, then I could do BC or CB. All right, and that's it. There are the 6 circuits, and you don't need to worry about any others. Another nice thing to note is that some of these are just going to be the reverse order of the other ones, and that means that the sum of the weights is actually going to be the same, so that will cut down on the addition that we need to do. So notice, for instance, this circuit, okay, this is A, B, C, D, A, and that's the exact reverse of this one. But it still involves the same edges. We still have edge AB, we have BC, we have CD, and we have DA. Okay, so we're adding up the same weights for both of those circuits. Okay, so those match. These two, these two. Okay, and then ACBDA matches this one. Oops, no it doesn't. Okay, these two match, and these two match. Alright, so let's find the sums of the weights. Okay, so for this first one, I have, call this number 1. Okay, so I have edge AB, which is 18, BC, which is 16, okay, CD, which is 11, and DA, which is 15. Alright, and then I have this pair down here. These two are going to have the same weights. Okay, so AC is 25, CB is 16, BD is 12, and DA is 15. Alright, and then I have the other pair of two matching circuits. Alright, and we've got AB, which is 18, BD is 12, DC is 11, and CA is 25. Alright, so if you add those, we get weights 60, 68, and 66. So the most optimal route would either be this circuit, ABCDA, or ADCBA. Alright, so sometimes an optimal solution is more than one route. Alright, so drawbacks to this method. Think about how many possible Hamilton circuits we'd have to list for a complete weighted graph with 10 vertices. Okay, well that would be 9 factorial, and that's 362,880. Okay, that's terrible. That's way too difficult to do by hand. One with 16, that would be 15 factorial Hamilton circuits. That's even more. Right? So we have a couple other options. We've got the nearest neighbor method, which gives an approximation to the optimal solution. So if the brute force method is too time consuming, then maybe we're okay with an approximation. And you'll find that in particularly large graph theory problems, sometimes these are good approximations. We're not talking about ones that are very far off. But let's say that a company has millions of dollars in the budget, and if they're trying to minimize travel costs for employees, then maybe they're okay with a solution that costs $100 more than the absolute lowest, if they can save a lot of money by not using this brute force method. Right? So even finding the solution costs money. If they have to pay a mathematician, or if they have to run a computer program, all the time spent running that program could end up costing more than just the $100 that they would need to pay to end up with a solution that's not quite exact. Alright, so in the next video we will look at 2 methods for approximating optimal solutions. We have the nearest neighbor method and the cheapest link algorithm.